Hi, good morning. Today we will see binary search tree operations. In the last class, we have already seen how to insert an element onto the binary search tree. Now we'll see binary search tree deletion as well. The last class we have seen inserting how we can insert an element onto binary search tree. For example, in the case of insertion of a value 38, we will be inserting it like this. We will be comparing the element that is coming for insertion with root node. If it is less than the root node, it will go in the left hand side, left child. If it is greater than, then it will go to the right child. So 38 is greater than 30, it will go to the right child. Greater than less than 40, it will go to the left side. Greater than 35, it will go to the right child. So the insertion will be like this. And we have already seen the insertion procedure as well, recursive procedure and iterative procedure for insertion. So for inserting an element, first thing what we do is we will search for that element in the BST. If it is not present, we will insert it as a left child or right child of a particular leaf node. Now let's see how we can delete an element from a binary search tree. Let's take this sample binary search tree. Let's say we would like to delete the key with value 25. So this is the element which we would like to delete. Once again, the first step is to search for this key value 25. If it is present, then only you can delete. Otherwise, we say that the element is not present. In order to delete this, what we need to do is we need to remove this and we need to set this pointer as null. So you search for the element 25 in this entire tree, and if it is found, then you set this parent pointer as null and delete this node. That's it. Suppose you want to delete key value 43, then also you do the same procedure. You will search for this key value 43. For example, in this case, you will come here. 43 is greater than 30. You go here. Greater than 40. You go here. Which is less than 45. You go here. Which is greater than 42. You go here. Yeah, you found 43. Now you delete this parent link and set this as null. So the previous two delete cases were simple, as we were deleting the element which is a leaf node. There is no more things to be cared. But for example, in this case, we would like to delete an element which is having a key value 42. In this case also we will search for this 42, and the same procedure you can apply. You can delete this node and you can set this to null, but we have one node 43 which is left at this position. So somehow we need to incorporate this. So 43 need to be used as a left child of 45 in this case. So you can do something like this. You, instead of deleting this node, you can use 43 at this position, or 43 will take the position of 42. It's having only one child, so that's also another easy case. If a particular node is having only one child, you just delete that node and you take this as the the only one child to be taking its parents position. Then once again the BST property will be satisfied. But it will not be the case if the element which we are going to delete is the root node, or if the element which you are going to delete is having both left and right child. If the element you are going to delete is not having any left and right child, or if it is a leaf node, then the deletion process is easy. For example, deletion of 10, 25, etc. You just cut this parent pointer and delete this node. If it is having only one child, then also the procedure is easy. For example, if you delete this node 42, then 43 can take 42's position, and then everything will be okay. For example, if you're deleting 45, then also it is okay. You take you would you make 42 to take 45's position, then 42 and 43 will be its right answer. But if the element which you are going to delete is having both left and right child, then who is going to take the position of the deleted node, the left child or the right child? It can both can claim the position, but which one is going to take so that we have an efficient or a better representation of the tree? So that will be the case which we are going to analyze next. Let's say you are going to delete the element 30, then you can either bring 20 as the to take the position of 30, or you can bring 40 also to this position. But we need to do lot of rearrangements. If you are bringing for 20, then you need to consider 25 again, and you make 25 to the right side of 20, so that you need to make lot of rearrangements. So the best option that you can think of is the position that is going to be taken by 30 will be the in order predecessor of 30, or in order successor of 30. That will be the best choice if you are if you're giving this position to, so that there will not be any rearrangement. For example, instead of while deleting 30, either 25 can be brought here or 35 can be brought here without altering any other elements position. So if you bring 25 here, 25, 20 and 10, 20 is less than 25, 10 is less than 25, so everything is okay. Here also everything is greater than 25, so that is also okay. So you can bring 35 also. If you bring 35 here, all the elements on the left side is less than 35, and all the elements in the right side is greater than 35, so there also it is okay. So in order predecessor or in order successor, that will be the best option if you are taking. So if you're considering the without altering any other elements position, in order predecessor will be available in the rightmost position in the left subtree. You are going to delete 30, so you consider this left subtree, and the rightmost position you can get the in order predecessor. There is no need to do an actual in order traversal for finding the predecessor and successor. You can find it very easily by taking the rightmost element in the left subtree or the leftmost element in the right subtree. In order successor will be available in the leftmost position in the right subtree. Sorry. So you can see the procedure for deleting a binary search tree. An element in a binary search tree. If p is null, we are passing the root pointer here. If p is null, then you can return null. There is the tree itself is empty. If p pointer left child is null and p pointer right child is null, means that there is only one node, that is only root node is available. Then if p is root, then you make root is equal to null and free p. So there is the meaning is this. Meaning is this: if there is it's having only one node, it's the root node itself. So you just delete the root node. Now the tree is empty. Otherwise, if key is less than p pointer data, then you do a search procedure in the left part, and you call this procedure delete procedure recursively. If key is greater than p pointer data, then you call the procedure recursively in the right child. So delete p pointer left child, delete p pointer right child. If key is less than data, then delete left from left child. key is greater than data p pointer data, then delete from right child. Then you can consider one more thing here, that is the height of the left child and the height of the right child. For example, while considering the in order predecessor or in order successor, which one you need to consider? By considering the left child, left subtree and the right subtree. For example, in this case, the left subtree is having smaller height and the right subtree is having larger height. In that case, in order to make this tree better representation, you can take the element from the right subtree, so that or by you can try to reduce the height of the total tree, total BST. That is, if height of the p pointer left child is greater, that is if the left child is having larger height, then we will use in order predecessor. We are assuming that there is a function which gives you the in order predecessor from the left subtree. If the height is of the p pointer right child, that is the right subtree is greater, then we will be using the in order successor, so that we would like to make the tree, make the BST balanced. We will use this height concept. We are assuming that you have a function which gives you the height of the left child, height of a tree, which by giving the point root point. Now there is one more thing to be considered, that is while considering the in order predecessor from a left subtree, we may have to recursively delete some more elements from here. That's this procedure, that is recursively delete p pointer left child again. That is, in this case, let's say we had some more elements here. We had a right child for 35. Let's say we have a right child for 35, and the deletion was for the key value 30. Then the in order successor which will be considered will be 35. So we are going to bring 35 to here, 30, but it has a right child. So we need to recursively call the same procedure, so that the this also this the while deleting 35, that also incorporated. So that is this step, that is recursively call this delete procedure at the p pointer left child as well, while considering the in order predecessor. While considering the in order successor, we need to delete the right child as well. So for this value to be the in order successor, it should have only left child here. For this value to be in order successor, then this will be having only right child. So that is what it is mentioned here. So if you're considering in order predecessor, then you need to call the procedure if there is a left child. You need to call the same procedure if there is a right child. So that is how we delete an element from a binary search tree. For example, this is just a concept in which we would like to discuss about the drawbacks of binary search tree. Uh, let's say we have the same set of sorry, two same set of elements, that is 40, 20, 30, 60, 50, 10, and 70. Then if the keys are coming in this order, in this sequence, then the tree, the by BST will be created like this. so that you will be having a height of the tree is equal to 2, and the uh, time taken will be order of log n, or the search operation can be done in order of log n. But if the keys are coming in this order 10, 20, 30, 40, 50, 60, and 70, then the tree that is constructed will be in this way. That is, it will be something very similar to a linear list. So the procedure is going to take order of n time for search. So as I have told in the beginning, we don't have any control over the height of the binary tree. The height of the binary search tree is controlled by the sequence, or the sequence of arrival of the keys. So the sequence of arrival of the keys is also related to the search procedure here, or the sequence of arrival of keys is going to control the height of the binary search tree. So that's all about binary search tree. We have seen binary search tree and its properties. Then how we can search in a binary search tree. In a binary search tree, the search operation is very similar to binary search. If the element is less than the root node, we'll be going to search in the left part. If it is greater than the root node, we'll be going to search in the right subtree or right part. And we have seen how to insert an element onto a binary search tree and how to delete an element from a binary search tree. It's recursive and iterative procedure. So that's all about binary search tree. Thank you.